Hi, everyone, and welcome to this webinar. Today, we're going to talk about how developers can stay productive while dealing with security constraints that typically come with cloud native applications. So, imagine that your app is running in Kubernetes, but you need to access components in a public cloud like an S3 bucket or a serverless database. So, we're going to take a look at how to set up AWS IAM policies from Kubernetes using IAM rules for service account or RSA, how to secure your application with network policies, and how to restrict egress connection using domain names as opposed to IP addresses. As you can imagine, configuring all that is not a trivial thing. So we're going to see how this can be simplified by using a different approach based on declarative intent. And of course, all this with a real example and a hands-on demo. So let's get stuck in. My name is Nick, and I'm the head of DevRel here at Otter. Our company focuses on making life easier for both developers and SecOps teams by creating open source tools that everyone can love. Ultimately, we want developers to spend less time on those complex security configurations and more time coding, while also ensuring adaptive and continuous compliance for the security team. And we achieved it through automating identity and access management. So now a little bit about me. I spent the last 7 years knee deep in the world of Kubernetes, wearing all sorts of hats along the way. I've been doing everything from engineering to product management and finally developer relations for the last couple of years. I've been lucky enough to work with all sorts of companies, from tiny startups to giant tech behemoths. I've tackled everything from networking and security to distributed storage for stateful applications, Kubernetes cluster lifecycle management, and even scaling things out to the edge. Indeed, it's been a wild ride. So, what's the plan for today? We're going to follow Otis, our first Otter developer, on his journey to developing and deploying a microservices application in Kubernetes. Now, the thing is, the security team asked him to make sure his application is deployed with zero trust in mind. Since he's using resources in AWS and accessing public APIs, he needs to make sure he's applying the least privilege principles when configuring access to these components. The problem is, this is going to take a ton of time since Otis isn't an AWS expert and isn't sure how to apply the best security practices in his Kubernetes cluster. He's feeling pretty frustrated about it, and I'm sure we can all relate. But there's no way around it because Kubernetes isn't secure by default, and the data shows we can't leave the cluster and the application open to potential attackers. Let's take a look at some numbers. Cybersecurity Ventures believe that cybercrime damages will triple between 2015 and 2025, reaching a staggering $10.5 trillion. That's 10,500 billions. This is absolutely massive. And it explains why companies are starting to invest heavily in security tools. It also explains why we are seeing the emergence of new governance programs like the European Cyber Resilience Act, which sets legal cybersecurity requirements for both hardware and software products sold in the European Union. If we focus specifically on cloud-native environments, a 2023 Red Hat report tells us that misconfiguration is still a top concern when it comes to security. And with 94% of organizations who experience at least one security incident in 2023, it becomes pretty easy to connect the dots between misconfigurations and those security events. Now, consider that platform security really begins with how developers deploy their code. Without the right configuration tools and processes in place, well, securing your pipelines can feel a lot like playing Russian roulette. But it's not just about developers. Every team involved in the software development lifecycle has its own set of responsibilities and challenges. The infra or platform team, for example, is constantly worried about securing the entire environment. It starts with workload identity and access management, IAM, and if a component gets compromised, they need to make sure the damage is contained. This means minimizing the attack surface and stopping any lateral movement. They typically adopt a zero trust approach where there's no implicit trust within the internal environment. All workloads and user interactions have to adhere to security principles as if they were out in the wild, so to speak. It's like treating everything inside the company as if it were on the public internet. Nothing gets a free pass. Then we have the engineering team. Their job is to make sure the code itself is squeaky clean. This means checking that their dependencies don't have any nasty vulnerabilities or hidden malicious code. They also need to keep their software bill of materials, SBOM, up to date and lock down their CI pipelines to prevent any credential leaks. Ideally, they'll be using short-lived credentials whenever they access cloud services just to be extra safe. Next up is the security team. Their job is huge. They have to define and enforce all the compliance rules. But more importantly, they need to make sure that every single deployment stays compliant over time, no matter what technology is being used. They're the ones who establish the root of trust, and if something goes wrong, they need to have the processes in place and know exactly who to call to get things fixed as quickly as possible. So it's widely understood that excessive security measures can hinder development velocity and often lead to longer sprint cycles. The CISO is usually the one who embodies this concern the most. Faster development cycles can be scary for them, as it's often hard to keep up without causing frustration among developers, especially with limited staffing. Plus, Kubernetes can be quite complex to secure. First, it's a constantly evolving platform, and security concept can change over time. Take, for example, the deprecation of pod security policies in favor of pod security admission, two completely different approaches. And second, with the proliferation of operators and custom resources, the potential impact of a security breach has become gigantic. So, how do we find a compromise between security and the pace of innovation? Well, we can take a cue from Kubernetes, a platform that excels at enabling the creation of other platforms on top of it. What we need is an asynchronous way to express security requirements with the right level of abstraction. This means treating the implementation details of security domains as interfaces beneath a declarative model. This model sits on top and provides users with high-level, human-readable configuration, essentially a declarative intent that's easy to set up and understand. Okay, that might seem simple on paper, but to really understand how far we've come and see all the different configurations involved, let's first take a look at the manual approach. We'll follow Otis through his workflow. His mission? To integrate a DynamoDB database into his application stack running on EKS, and then use the OpenAI public API to add a chat completion feature. The security domains he has to tackle are pretty extensive. He needs to set up Kubernetes RBAC to create service accounts, IAM roles to access the DynamoDB table, Kubernetes network policies to keep the application services locked down, and figure out how to implement egress control so he can limit external access to only the public services he actually needs. That's a lot for an otter to handle. But first, let's take a look at what Otis actually has to do before he can even start writing code. We'll begin with the AWS requirements and then follow up with the network security aspects. So here on the lower left, you have the application's architecture, which is a dad joke generator. Of course, it's a bit overkill. It's composed of a lot of different microservices, but that's obviously for illustration purposes. So the idea is the following. The user is requesting a joke from the joke server. The joke server itself is running as a web server written in Go and serving the joke endpoint. To get the joke server is publishing a message on the NATS queuing system. That message gets picked up by the joke worker who is subscribing to that particular queue. And then the joke worker will do two things, actually three things. It's gonna call the OpenAI API to generate the joke itself. Then it's gonna store it into both Redis and DynamoDB, and finally sends the response back to NATS. And then the joke server received it and serviced to the user. Next, we need to configure the various components of IRSA, starting with the IAM role. So we need to create a role with two particular dimensions to it. First, the permissions policy, where we specify we want to allow specific operations on our DynamoDB table. So here we allow every operations for DynamoDB. And we want to apply this to a particular resource that should, in theory, be the table that you want to manage. Here I've specified a wildcard because the full ARN wouldn't fit in the screen, but it's just for illustration. But typically, you would specify the ARN of the DynamoDB table that you want to manage. Then you have the trust relationship, which is key in terms of IRSA configuration, because it's establishing a trust relationship between your EKS cluster, or more specifically here, the OIDC provider of your EKS cluster, and the web identity token representing your service account. So this web identity token is mounted within the pod that is accessing the DynamoDB resource. So it contains the service account's ID here that you can see, as well as the audience, which doesn't change from one configuration to another. Then on the left part here, this is where the magic happens, because you are running in an EKS cluster. So within the control plane, there are some specific components that guarantees that as soon as you annotate the service account attached to your pod, then a couple of things will be available to that particular pod. So you will see that, and we're going to see in the demo later on, that you will find a couple of environment variables that will be available to the pod, including the web identity token, the AWS region, and a couple of other things. So it's a two-step process. First, you create a service account. This is where you also have to be mindful about the RBAC configuration for your pod within Kubernetes, so a different security domain. We're talking about Kubernetes RBAC. So when you create the service account, you want to allocate and attach the right permissions to it within Kubernetes so that it's not overloaded in terms of permissions to the Kubernetes API server. So here we're talking about permission to the API server, not to AWS, right? This is a security domain for configuring the service account. But as soon as you annotate that service account with this particular role ARN, and then configure the pod or the deployment or any controller with that specific service account attached to it, then EKS knows that the application running in the pod needs to access a particular resource in AWS, and the STS service here will be validating the identity of the service account through this trust relationship. And then just after that, the pod, or more specifically the service account, will be allowed to assume that particular role and be allocated short-lived credentials to realize the operation on the desired resource. So in our case, DynamoDB. And this is it for the AWS part. Next, let's move to the network configuration. Network security configuration. So here from left to right, we need to restrict a couple of things. So first, we need to allow users to connect to the joke server. So all the network policy, of course, will be created in the application namespace. I've described here a portion of the configuration, the relevant part only, not the full manifest. So this particular configuration, by matching the pod selector app joke server without anything else, will allow anyone basically to connect to the joke server. So that's one security policy. The second network policy is for NATs. So NATs, we can see that we have two microservices accessing it. We have the joke server and the joke worker. from the ingress, right? Ingress to the NATS message queuing. So ingress from pod selector matching label joke server and from pod selector matching label app joke worker. That's the second network policy. We don't specify a port here and protocol, but of course, this is something you can do as well. Then next one, we have Redis. So as you can see on the picture here, only joke worker needs to access Redis. So same principle, ingress from app joke worker is only allowed. As soon as you create a policy that allows something, you have a default deny for that particular component. So here, just by allowing the joke worker to access Redis, it means that if anything else trying to connect that is not explicitly defined in the policy won't be allowed to do so. And finally, the last part is on the egress side, right? We want the joke worker to connect to OpenAI API and to AWS, to DynamoDB, right? So in first, we had how to authorize the joke worker to connect to the particular table via, IAM permissions. But here we're talking about network security. So we need to create egress policies. But unfortunately, Kubernetes-native network policy don't support describing DNS names. So we have to derive the IP addresses from the particular DNS names. So which means that if those IP addresses changes by any chance, we need to update that. We're going to see how with one of the operator that we're going to talk about in a moment, we can kind of automate that. But for the moment, if you want to do that with native network policies manually, unfortunately, you have to specify IP blocks for OpenAI API and DynamoDB. And since there is a good chance for load balancing and have multiple IP addresses, you need to update that. This is why here you have so many of them. So you need to find a way to find those IP addresses by yourself or by using another tool. So now let's sum up the challenges that come with this configuration workflow. First, you can easily picture Otis spending hours meticulously crafting network policies, only to find out that it made a tiny typo that leaves a critical resource wide open. And this isn't a one-time thing. It's error-prone at scale and requiring constant updates as the code base changes. Plus, only developers truly understand the actual communication patterns of their code. So simply taking away policy configuration from developers to platform teams doesn't solve the problem. While it might seem like a quick fix for the platform team, they don't have the same deep understanding of the application's inner workings. It's like trying to navigate a maze without a map. You're gonna hit dead ends and make wrong turns for sure. The platform team can't effectively secure what they don't fully understand, and that's where the real challenge lies. But at the same time, we can't keep the entire cognitive load on devs. They'd be forced to learn new skills as well as new languages just to define security policies for all these different environments. And crafting these policies is incredibly time consuming, which is taking valuable time away from what devs do best, building awesome features. And not to mention, it comes on top of what they already have to learn in terms of their usual CI, continuous integration tools. And also, let's face it, most developers aren't security experts. In large organizations, expecting them to become fluent in all this security jargon is just unrealistic. So platform teams often end up building an abstraction layer, but that's a massive undertaking to maintain. And even then, there's no guarantee that it will scale effectively or meet those strict security standards. So all these common problems are why we need a new standard for developers to express their requirements, but at the same time without letting the platforms and security team out of the loop. That's where intent-based access control, or IBAC, comes in. Instead of manually configuring policies for every service and environment, IBAC lets devs simply declare what they need access to. Whether it's a DynamoDB table in AWS, a Kubernetes service, or even a traditional database like Postgres, IBAC automatically figures out the right access controls based on those intents. So this approach not only simplifies the developer's life, but also makes things easier for the platform team. By abstracting away the complexity of policy configuration, IBAC frees them up to focus on higher level security concerns. So IBAC is built on the power of Kubernetes operators and as well as a declarative model, leveraging the strength of the platform to create a more streamlined and intuitive security workflow. So let's take a closer look at how Otis workflow changes with IBAC. At the core of IBAC is client intents, a Kubernetes custom resource that represents the developer's intent. We'll follow the same steps as before, granting access to the resources that the datjokes application needs to function properly. We start by defining the client, or source service, which in this case is the joke worker. First, it needs access to NATs, the messaging system, so we simply add NATs to the list of calls. Then, the joke worker needs to access Redis for caching jokes, so we also add this to the list. Next, we handle egress connections by simply specifying the domain names. This will be translated into IP addresses later on, which we'll see in detail during the demo. And finally, we request access to the DynamoDB table by entering its full ARN. And in this case, no wildcards is needed. We also specify the actions we want to authorize. In this particular case, we want to allow all possible operations. And that's it. We've accomplished the same thing as before, but using a much more standardized and intuitive approach. Plus, this client intent can easily be submitted to the platform team as a pull request in the appropriate repository, or even collocated with the code to trigger a GitOps workflow for validation and deployment. We could even imagine adding an external admission controller like Kyverno to perform additional compliance checks during the CI workflow. But most importantly, we've just opened up a world of possibilities in terms of automation and processes to ensure a safe production deployment. So, how does client intents work? The abstraction provided by client intents is generic enough to enable policy as code across multiple security domains. The type field describes the target domain, allowing client intents to extend its interface to many use cases. We've seen network policies and IAM roles, but for example, you can also specify layer 7 policies if you have Istio deployed. And as mentioned earlier, other valid types include multiple hyperscalers as well as database solutions. And since it's open source, we hope the community will come up with new use cases to enrich client intents capabilities. Secondly, IBAC doesn't just set and forget. It's constantly watching your application's traffic patterns. If it detects something new or unusual, like a service trying to access a new resource, it can automatically create a pull request in your client intents repository. This means you're always in the loop, able to review and approve any change before they're applied. Thanks to the combination of policy as code and real-time updates, the IBAC workflow ensures your applications stay compliant over time. As your codebase evolves, your security policies evolve with it. This adaptive approach means you can confidently deploy new features and updates without worrying about introducing security holes. Okay, that's enough theory for today. It's time for Otis demo. And if it doesn't work, you can blame him, not me. So the first thing I want to show you is the different components of the solution, as we mentioned before. So you can find here first the credentials operator. Its role is to deploy the IAM role in AWS in our particular case. The intents operator is monitoring the client intent custom resources and reconciling that resource within the Kubernetes cluster to reflect the desired state. So when we are going to create client intents, those will be translated into lower level security rules. So whether it's network policies or allowing permissions on the IAM role. Then we have the network mapper. Its role is to map out our application to detect what components are talking to what other component with the help of the sniffer, which is monitoring as a daemon set what is happening in the cluster using BPF technology. Okay, next I want to show you the IAM integration. So let's jump into the namespace view. You can see that I don't have any dev namespace, which is the namespace where I'm going to deploy the application. For that, we're going to be using DevSpace. So if you don't know DevSpace, it's an application lifecycle tool from Loft. You can check it out on their website. It's really powerful. And as part of the application deployment, I'm deploying some custom resources, including the client intent for the joke worker, which contains the requirement to access my DynamoDB table. So now let's deploy that application. For this, we go back into the DevSpace folder and just run DevSpace deploy, which is going to create a new namespace that contains all the application components, including the Redis cache, the Redis operator, which deploys the Redis cache, the NATS operator, which deploys the NATS message queuing system, and then the joke worker and the joke server. The joke server is waiting for NATS to be ready to get out of its crash loopback phase, which should happen in a couple of seconds. Okay, so now everything is running, and if we check the client intent, we should see also the joke worker client intent, which requires access to the DynamoDB jokes table here. Then to allow the credential operators to effectively create the IAM role, we need an extra label in the application, in the joke worker, which is that one. So credentials operator.authorize.com create AWS role to true. By doing this, we are telling the credentials operator, please go ahead and create the corresponding AWS role, also create the permissions and the trust relationship. As soon as this is ready, the role is going to be created. And then here you can see that the annotations now contains the RN of the role that is created. So obviously you can do this manually, or as I did it today, I just included the labels into the application template. So now let's check that in AWS, the role has been created, permission and trust relationship attached. So now we are in AWS here. And if I check for the role, this is the one I want here. And if I refresh it, I can see that permissions policies have been attached and contain the resource I need to access, as well as the action, and the trust relationships contain all the relevant information. Now let's check the DynamoDB table, which is here. That's the joke table. If we go explore table items, we can see it's currently empty, and we'll go back there later when we'll generate joke to see that they've been recorded in the table. Okay, now, so let's go back to our console and let's apply the remaining client intent. So they are located in the policy folder. This is the client intents.yaml file, and let's take a look at it. So if I start with the beginning, I've got the joke worker that now also includes the internet domains I want to reach, the joke server that needs to access NATs, Redis that needs to access itself as detected by the network mapper, the Redis operator that needs to access the Kubernetes service in the default namespace. Okay, and that's it. So now let's apply that. But first, we need to delete the existing joke worker, client intent. Okay. And now we're ready to deploy all the client intents. Here you go. So now let's check the client intent list, and we should see a lot more of them. The joke server, the joke worker, Redis, and Redis operator. And as a result, now I should also see some network policies that have been created. So those are the ingress network policies for NATs and Redis. We can see that the rule applies to ingress from the namespace selector dev, so within the dev namespace. For all the pods that match the label here, access NATs dev true, will have access to NATs. And for the Redis access, it's pretty much the same thing. Namespace selector dev, for all the pod that have this label, access Redis dev, then access to Redis is true. Okay, so now let's check that the application is effectively working. For this, I need first to make the server available locally. And now let's request some jokes. So we're just gonna create a loop for that. And we want, let's say, 10 jokes. Okay, it seems to work. We can also check the logs of the worker. It seems all good. We can see the log of the server, no error message here. So this seems to work. So now let's check that in AWS, the DynamoDB table is populated. Here we're back in AWS. If I just refresh the table, I can see all the jokes have been stored. So both the network policies as well as the IAM permissions have been configured correctly. Now, I just want to show you the bit of code that effectively writes into the jokes table and makes use of the web identity token. Let's take a look at the code. For this, we go into the internal AWS folder where I've got this bit of code here that connect to the DynamoDB table. And as you can see, I'm just loading the default config, which normally should be the shared credentials. But in the pod, I don't have any shared credential store. So the SDK is intelligent enough to understand that if there is the web identity token environment variable that is populated, then it's going to use that to connect to AWS, as easy as that. So it's totally transparent for the code. The last part I want to show you is the egress control. So for that, let's go back to the policies. Here I've got a quick script to enable egress. And before running it, I want to show you the difference in terms of the network policies that are going to be generated. So of course, the client intent will stay the same, But the network policies will change since we are going to introduce egress network policy as well, primarily to control the egress domain name that we allow the application to interact with. Okay, so I've deployed the modified version of the Helm chart, and now we should see more network policies. The one we are interested in is really the joke worker, which is accessing OpenAI and AWS. So we can see that we have IP addresses block that have been set up to represent both OpenAI and AWS. And if we look at the corresponding client intent, the joke worker, if we describe it, we see that as part of the status fields, this is where the resolved IPs appear here. This portion is updated by the network mapper. However, in the client intent spec, we can still see the domains only. So this is how we resolve the domain names, by using the status field and updating the network policies with IP addresses. And there's one last thing I wanted to show you. I've just mentioned that the network mapper had generated the client intent. So how to do that? Well, you can use the authorize command line using the network mapper argument, export. You just specify the name of the namespace. And here you go. This is the current communication patterns detected in my application. Then you can directly apply these manifests into your Kubernetes cluster, and you're good to go. That concludes our demo for today. Now that we've seen IBAC in action, let's talk about why this is a game changer. What are the real benefits here? First up, time to production. Remember how we talked about those frustrating delays waiting for manual security reviews? Well, with IBAC, those bottlenecks become a thing of the past. Deployment velocity skyrockets because policy enforcement is automated and happens in real time. Developers can push their code with confidence, knowing that security checks are baked in every step of the way. Second, and just as important, security posture. Instead of security being the bolted-on afterthought, it's now integrated directly into the development lifecycle. It's part of the DNA of your applications. This means you're not just reacting to security issues, you're proactively preventing them. Then, attack surface minimized and locked down. Think of IBAC as a security shield that actively protects your applications. It goes beyond just preventing misconfigurations. It continuously scans for potential vulnerabilities and automatically applies the right policies to lock things down. This significantly reduces your attack surface, making it much harder for attackers to find a way in. And if a system does get compromised, IBAC limits the damage by preventing that infection from spreading. It stops attackers from moving laterally within your environment, keeping them contained in minimizing the overall impact. Finally, developer focus, laser sharp. We all know that developers are happiest when they're coding, not wrestling with frustrating security configurations. IBAC and client intents take that burden off their shoulders, automating those tasks and letting them focus on what they do best. This means faster innovation, quicker feature delivery, and a more productive development team overall. It's a win-win for everyone involved. So now, let's recap the key takeaways from today's deep dive into IBAC and client intents. First, security is a team sport. We've seen how the burden of security can't rest solely on the shoulders of developer or the platform team. It takes a village. Developers and security teams need to work hand in hand to build applications that are both agile and resilient to attacks. IBAC empowers that collaboration by creating a shared language and a common framework for security. And that is the future. The old way of manually configuring policies just doesn't cut it anymore. If you want true zero trust and continuous compliance, you need tools that are autonomous and adaptive. IBAC's declarative model gives you exactly that. a way to define your security intention, and then let the system handle the complex enforcement details. It's like having a security autopilot that keeps your application safe, even as they evolve and scale. And last but not least, empower your developers. Don't frustrate them. Instead of seeing security as a roadblock, IBAC helps developers understand and embrace it as an integral part of their work. By giving them the tools, like client intents and visibility they need, you can turn them into security advocates, proactively identifying and mitigating risks throughout the development lifecycle. This shift in mindset not only improves the security posture of your organization, but also fosters a culture of shared responsibility where everyone plays a role in keeping your application safe. Now, I'm going to ask you for a favor. If you liked what you've seen today, please get involved in those open source projects. Maybe start by going through our tutorials that provide a hands-on opportunity to explore this concept further. Or don't hesitate to join our Slack community if you want to reach out to me directly or just asking questions. And finally, if you want to get even more information on the AWS IAM integrations that we've seen with DynamoDB today, you can check out my comprehensive blog post I wrote a couple of weeks ago. Thank you for watching. I'll see you in the next one.